both x and mu are vectors, because in the, as we said before, in the multinomial distribution, we are going to use 1 of k coding to denote the variable x. So the data likelihood is suppose the length of this vector is capital K, which means that we have k outcomes. Remember the trick we used in Bernoulli distribution. We are going to write this part into mu k, nk, where nk means the number of samples whose x takes the outcome k. This is the data likelihood. Now we want to impose a prior distribution over the parameter mu, which we are going to use Dirichlet distribution. So p mu vector parameterized by alpha vector. Alpha vector is a parameter in Dirichlet distribution. This is the definition of Dirichlet distribution. We know that the posterior p mu given d is proportional to data likelihood and the prior probability. So we put the Dirichlet prior and the data likelihood into this part. We get by the way, this part here does not involve mu, so it is a constant. We can drop it. So finally, p mu given the data set is proportional to this quantity here. To turn this proportion symbol into an equal sign, we need to add a constant to make this probability a valid definition of probability. So to make equals to 1, we can add a constant, and the constant turn out to be gamma function. And this is a Dirichlet distribution, right? And the parameters are now nk plus alpha k and nk plus alpha k. Because it does not involve mu. So here we are talking about mu here. So if our term does not involve mu, we can drop it. So by doing this, we show that the prior probability, P mu given alpha, and the posterior of mu, P mu given data D, are both Dirichlet distribution. So we say Dirichlet distribution in this case is a conjugate prior. And because the two models data, we use multinomial distribution. And this multinomial distribution ensures that this property is satisfied. So we say Dirichlet distribution and the multinomial are conjugated to each other. Any questions here? What is gamma? Gamma is a function. Yeah. It's like, this in the right part. Any questions about the conjugate prior?
How do you know that P mu given D integrates to 1?
P mu given D, because it is a probability, it must integrate to 1.
Yeah.
Right.
Just the question asked. By adding this Dirichlet prior back, you're making it a probability.
You mean how this quantity here integrates to 1?
Right.
Actually, I don't know, but this is the definition of Dirichlet. It must be valid, but I don't know how to do it. So in this new distribution, the parameter is again a vector. Its component is nk plus alpha k. If you check this with the definition of Dirichlet distribution, you can see that this is also a Dirichlet. And finally, let's see a little bit about the estimated bias. The definition of bias is we have a parameter theta, and we have an estimator theta hat. The estimator could be MLE, MAP, or second order moment estimator, whatever. So the bias is defined as the difference between the true parameter theta and the expectation of theta hat. This is the definition of bias. So why we have an expectation here? We know that expectation must be defined with respect to some distribution. So here is something like this. From the true distribution Px, which is a null, we draw a center of samples D1. X1, I just put subscript 1 here. Means the sample is from the first bench. We can draw the second bench of samples from this distribution, and similar do it for many times, like m times. For each of this D1, D2, and Dm, you can get an estimation of theta 1 hat, theta 2 hat, and theta m hat. And we have a probability over this data set. So we have a probability over this quantity. Now we can define our expectation of this estimator. Because each of these estimator, C1, C2 head, C_m head, has a probability. So the expectation of the C head is P C2 head. Implies. Because it is expectation, so M must be infinity, which means that you draw infinity bands of samples. For each of the sample, estimate a value, and plugging it into here, you get the expectation. This expectation quantity here basically states that if you have infinite number of samples, what will be the value of your estimator? And this quantity, the expectation, the difference between the true parameter and the expectation here is called the bias of this estimator. If the bias term equals to 0, this estimator is called unbiased estimator. If it is not, it is called biased estimator. Next, I'm going to show you an example. Before doing that, do we have any questions here? So suppose we have a distribution which is a Gaussian, parameterized by mu and sigma square. We draw a set of samples D. Each x is from this Gaussian distribution. We know that under the MLE estimation, mu hat equals to this is the maximum likelihood estimation of the expectation parameter mu given this data set. Let's check whether this estimator mu hat is biased or not. So by the definition of a biased estimator, we need to compute this bias term. So it is mu minus expectation of mu hat. This is the bias term. We are going to check it. If it is 0, we say this estimator mu hat is unbiased. Otherwise, it is biased. So expectation mu hat equals to 1 over n EXI, right? According to this property of expectation, we just move this expectation into the rightmost part. And we know that each of the xi are independently drawn. And it is drawn from a Gaussian distribution. So the expectation term here is simply mu, right? So 1 over n mu equals to mu. So the bias mu minus mu equals to 0. So this estimator mu hat is unbiased because the bias term is 0. Another quantity in Gaussian distribution is variance, sigma square. Under the MLE estimation, its estimator sigma square hat equals to 1 over n xi minus mu hat square. This is the MLE estimation of the variance. Let's check whether it is biased or not. So again, the definition of bias is sigma square hat. Let's look at this term. Expectation here I just expand the square term here. Is equals to 1 over n this is for the first term here, and 2 over right here is nothing but write the terms in the parentheses into write them separately. What is the term here? Xi is from a Gaussian distribution. Remember that we have a property that variation of a random variable is defined as ex squared minus ex, the square of the expectation of x. These two are different. So ex squared equals to the variance of x plus the square of its expectation. So using this property, this term here is the variance of a Gaussian variable is sigma square, and the expectation is mu, so it's sigma square plus mu square. And these two cancels, because we have n sums here and divided by n, and this is a constant. So these two are cancels. And here for this term, NO, look at this quantity here. It is mu hat, right? The definition of mu hat is something like this. So here it is mu hat. So this would be mu hat square, the expectation of mu hat square. And plus these two cancels. All right. So we got sigma square plus mu square minus the expectation of mu hat square. Let's take a look of mu hat square. By definition, mu hat square equals to 1 over n square, I equals to 1 to n, j equals to 1 to n, xi, xj. plug in the definition of mu hat. And this term becomes I equals to 1 to n xi squared plus j equals to 1 to n, but j does not equals to I, xi xj. We decompose this part into something like this. On this part here, xi and I and j are not are different. So we move the expectation into inside. We get 1 over n squared, I equals to 1 to n. Expectation xi squared j does not. And this term again is mu squared plus sigma squared. Because we assume all the samples are independent from each other. According to this property, if x, y are independent, the expectation of their product is the product of their expectation. So this term here is EXI, EXJ, which is mu squared, right? And we have n minus 1 times mu squared. And we have n times here. So this equals to mu squared plus one over n sigma squared. Let's plug in this term into here, and we get the sigma squared plus mu squared minus mu squared sigma squared, which equals to 1 minus 1 over n squared. And remember, this is the definition of this quantity here. So we plug this definition into the bias term. We can see that the bias equals to is there a mistake here? Right. So this would be 1 over n sigma square. It does not equal to 0. So the estimator of the here. So the bias of the estimator sigma square hat does not equal to 0. So this estimator is biased. Any questions? So this is pretty much for today. If you have any questions, we can discuss later.